Yes. So, good afternoon. In the previous class, we were trying to understand about the electrocyclic reactions, right. So, we studied how the ring closure as well as the ring opening of electrocyclic reaction happens under heat and light. We understood the Woodward-Hoffmann rule. Using Woodward-Hoffmann rule, we studied their stereospecific products are formed, like under heat it should be only Kohn rotation, depends upon whether it is 4n system or 4n plus 2 system. Same way we studied for electrocyclic ring opening reactions also. So, we have just widely touched the basic of electrocyclic reactions, and after that we tried to do some related problems on electrocyclic reactions, and we study some important biosynthesis of some molecules where you can where electrocyclic reactions are involved. Okay. So, today what I will do is that I will just take you one important type of electrocyclic reaction, that is Nazarov cyclization. After seeing Nazarov cyclization, then we can get into some problems of pericyclic reactions, where you can involve all your pericyclic reactions like electrocyclic, sigmatropic reactions, scope, Claisen, everything. Okay. So, initially we will just discuss about Nazarov cyclization, and then we slowly get into some problems in pericyclic reactions. Clear? Okay. So, we will see what Nazarov cyclization is. So, what Nazarov cyclization is about, take a system like, so it's what system it is? Yes, it is a 4 electron system, right. Just you have an OH, if you leave this, it is nothing but is a butadiene and it is a 4 electron system. So, what happens if I heat 4 electron system? What Woodward-Hoffmann rule says to you? What it says, what type of cyclization it can undergo, whether it is a Kohn rotatory or this? Yes, it is a Kohn rotatory. Very good. So, if you see this, you get this one, okay, you have a positive charge, sorry, you get this. So, you can get a cyclic product to OH, okay, but you will have an positive here. Fine, this is the simplest Nazarov cyclization. Okay. So, based on that, we will see one good example of Nazarov cyclization. What you do, we will take a simple molecule, so I have taken a system 2-cyclohexene connected by a ketone. Okay. So, if I close this one, so again what happens? It is nothing but again a 4n system, right. You have 2 electrons here, you have a 2 electron here. So, it is again a 4n system. So, what happens if you take this molecule and if you heat this in acidic condition, like for example, like if you put phosphoric acid in acetic acid and you heat this compound, okay, it undergoes a type of Nazarov cyclization to give you electrocyclic closure product. Okay, you get this nice. The important part is here about what you get this type of system. Okay, one hydrogen in another plane, another hydrogen in another plane. Okay. So, you get this product. We will understand this mechanism. Okay, we will study this mechanism in detail. First, when you take this system and if you heat it, you get this product which is a cyclized one, but you consider your 2 hydrogens. Okay, they are more important to see on. Now, if I take the same compound and if I irradiate this, basically if I photolyze this molecule, what it gives. If you see the product, just similar product, okay, but the important part is that you have to understand its stereochemistry. See, this case 2 hydrogens are different, and this case 2 hydrogens are same plane. Okay. So, if I take this molecule, if I heat, I get product A, but if I photolyze, I get this product B. So, I get 2 different products, and you know that why. So, what we will do now, we will try to understand the mechanism by which you get this product first on thermolysis, then we understand how we get this product on photolysis. Clear? Now, we will see what happens in thermal condition, how we got that product. What happened in thermal condition. And take my starting material. Now, if I take the starting material, and you know that I am doing this reaction in acetic medium, which I said in phosphoric acid and acetic acid. So, what happens? Your first step will be, what is your first step? Yeah, this, first write your first step, which you know, okay, get protonation, which you have studied, no problem with your first step. So, you know with your first step, it's just a protonation one. Then, yeah, you can just think about writing this structure. It can exist in this way also. Okay, so just making a resonance of it. Clear? Up to this, it's no problem. Okay. Now the important part is this: you bring your hydrogen now, which is going to tell about your rotation, the electrocyclic, which this is going to decide in your electrocyclic reaction. Now, what happens? You are heating. You know that it's a proper 4N system. Yes, it's a 4N system. So, what you studied in 4N system, like heating, yes, it is a con-rotatory. So, con-rotatory, both should be in the same direction, right? So, both should be in the clockwise. So, one of your hydrogen will be out and one should be in. Clear? One should be out and one should be here. And this you know. This part, you have to push your arrow here, and you know that. So, this happens inside. But this is the more important part. Okay? So, what you get then, if I you get a cyclization. So, one should be outside the plane, one should be in. So, I get 2 different things for con-rotation. Clear? Now, we will see our bonds. This should be, I have a double bond here and with a positive charge here. Okay. So, this is after your rotation. This is your electrocyclic ring closure one. This is the important one which decides your stereochemistry. Now, what happens to this product? So, you get this product. Clear? We got this product. Now, what happens? It's a removal of an proton to give me Okay, you get this, and then you can say this then undergo the enolization, ketoenol, then get your final product. Don't forget your hydrogens. These are the one which is going to tell the bar. See. So, this is the Nazarov cyclization which you do it in thermal condition. That is what the product we got. No? Initially we said that, remember, once you take this product and if you heat, you see you get an hydrogen with a double bond here. That is the product we got on this. Clear? This is on thermolysis. Okay. Same if you do in photolysis in the same condition, what happens when you do the same chemistry in photolysis? So, same reaction I am doing under photolysis now. So, I take my starting material, so I have my hydrogen which is important for me, okay, which is going to decide. So, now again we know it is H plus, so I can write that step which the protonation step. Then I can write like this. Clear? Fine. Now, from here it is important again. So, under photolysis, what you know? What happens under photolysis? This is what system? Previous case it was heating. So, heating 4N system, what? Con rotation. Photolysis, 4N system. Yes, this. So, you get this rotatory. So, it should be the same direction, okay. Opposite, right? This is opposite direction. So, one is clockwise, another is anti-clockwise. Then you know to bring this arrows. So, then both will be, now your both hydrogen will be out, right. Okay, you get this product. Now, you see your hydrogen, they are entirely different from the one which you got from the con one, heating. This is what in heating you got, this is under photolysis. Then you know your other two steps which we can write now. So, it is nothing but it is minus H plus followed by your ketol enol. Anyhow, we will write that. Then we get so we can enolize this one, but this is the interesting hydrogen. See, so you on the, so that's the Nazarov cyclization. So you take a molecule, okay, it's a 4N system, but if it is an enol 1, you take this, and you know that when you take this molecule on thermolysis, you get a ring closure. Even in photolysis, you get a ring closure, but they are completely different in their stereochemistry. Clear? Okay. So this is about your more about your electrocyclic reactions. Now what we will do is that we will try to now see some problems in pericyclic reactions, okay, which involves whatever we have read so far. Okay, we have studied all these reactions, right? Main reactions like we have did our sigma-tropic reactions, and we have involved cycloaddition reactions. We have seen now electrocyclic reactions. So what we will do is that we will just do some problems based on these reactions, and see like whether we can use our knowledge and we can apply them and solve these problems. Okay. So we will start with our first type of practice problem. This we call as, we say it's a rearrangement of benzocation into benzocycloheptatriene. Okay, this is benzocycloheptatriene. This is nothing but, you will see this is a diterpenoid. Okay, it's a diterpenoid. It is nothing but isosalvipuberline. Okay, it's a diterpenoid type of molecule. So we will see how this benzocaridine is converted into benzocycloheptatriene. Okay, involving different type of pericyclic reactions. Okay, first we will write the structure of benzocaridine. Furan, okay, and you have an iodine here, fine. So it's an aromatic compound with a methyl, fine, and you have a nice cyclopropane for this compound. Okay, clear with the structure. Okay, this is your benzocaridine. Now I take this compound, okay, I slightly heat this. So what you are going to expect now? So it's not about, I told you, it's not about only electrocyclic reaction. You have to think all about your pericyclic reactions, all the reactions. Okay. Okay. So what you are going to expect now? So you see, you have a system like this which you have studied in electrocyclic, right? So it's a, yes, it's a electrocyclic ring opening. Yes. That's all. So I can do nice electrocyclic ring opening if I take this compound, okay, because it is mostly under strain also. So it opens very nicely. So it's a electrocyclic. So your first step is electrocyclic ring opening. So electrocyclic ring opening happens here. So we will draw the structure then. Okay, once the ring is open, so it should be a 7-member ring. Then others are same. So I have a methyl here, I have a double. This will be exactly same, nothing will happen here. So you will add here. Okay, Now what happened here? So it's ring. So where you have the double bond, you have moved it across. So you have a double bond here, you have a double bond here, and you have a double bond here. You have a 2 hydrogens here. Clear? So you got this product. Now see the product. Now what it will do? Again, if I think on eating and photolysis, what you understand, what this molecule can do. Look the molecule, see the molecule, see these hydrogens. Do you think there is any possibility of this hydrogen undergoing some sigmatropic shift? Yes, it will undergo nicely 1,5 hydrogen sigmatropic shift. That's good. So 1, 2, 3, 4, 5. So I can push this and my hydrogen will be here. Clear? So can we draw the structure again? We'll take the nucleus and we'll draw the structure. So I will get my product of 1. So it's a 7-member ring. Okay, be careful with that. So this is fine. This all will remain same because that's not happening anything to that. And you have your furan, and you have your iodine with your double bonds unaffected. Now if you see after the shift what will happen. So I have a double bond here, and this double bond is not going to change. See? So if you see on 5 hydrogen shift, so I get this product. So what happens? It is 1, 2, 3, 4, 5 shift. So I get my hydrogen moved across here. Okay, it comes here. So my double bond shifts. Okay, I have shift in double bond, and it is moved to this place. So this is my hydrogen. This is 1,5 hydrogen shift. So interestingly, this molecule again undergoes another interesting reaction. What is that? Can you think what will happen again? Any idea? You can easily think about one. Anyone want to guess this? Can again think about 1, 2, 3, 4, 5. Say I can do another one more 1,5 hydrogen sigmatropic shift. Yes? See, I can nicely do another 1,5 hydrogen shift to give me my product. It's a 7-member ring. So this is where my hydrogen gets shifted. Clear? I have my double bond here. So I have a double bond with my methyl, and this part unchanged with my furan here and my iodine. Right? If you see the double bond, so I get this system. So, this is nothing but this is the benzocycloheptatriene system, benzocycloheptatriene system. So, you have taken a benzocaridine system and it undergoes 3-step reaction, 3-step cascade of pericyclic reactions. First, what it does on heating it does an electrocyclic ring opening, then it undergoes 2,1,5 hydrogen sigmatropic shift to give me this product. See how nice it is. This is the rearrangement of benzocaridine into benzocycloheptatriene. Okay, so you have now you know how to utilize your whatever you pericyclic reactions knowledge, and then you have to solve them. So, you have to see the system indeed, like you have to understand whether this system will undergo Diels-Alder or the system will undergo a co-prearrangement, or it will undergo electrocyclic ring opening or electrocyclic ring closure, sigmatropic reactions. This all should come into mind. Okay, clear? That is why we will do some interesting problems in pericyclic reactions, so that you will be, then you can do assignments and problems on that in future a lot. Okay. I will take the second sort of interesting system. Okay. Alkene. When you have an alkene type of system now. Okay, I am taking it this. Just don't get like once you see the system, don't get like really frightened or nothing like that. Just see the system, concentrate on your pi electrons. Okay, because most of the time when you are talking about pericyclic reactions, just concentrate on your pi electrons. Then decide. Okay. So once you see the system, don't get like really, oh, this system is hard or something like that. No, just see the system, see your pi electrons, and then you understand this. What this can do? Any idea? Anyone? See, if you see this pi electron 2, 2, 2, what is that? It is a 4n plus 2 system. Okay, it can do 4n plus 2 type of cycloaddition. Okay, what type of 4n plus 2 cycloaddition you are doing? You can do pi 2s plus pi 2s plus pi 2s, which you have studied. So, I can close this, I can use this bond to close this, I can use this to close this. Okay, sort of ring closure, that is all. See how simple it is. Now, if I close this, I want to close this one. So, I have a system like this now. Then I have this double bond, okay, which was earlier triple bond, now it has become double bond. You have this because it is as closed. Okay. Now we have a system like this. So you have a nice system like this now. See? This is nothing but if you want, I can. This is similar to B. If I write proper, can be similar to B. We are just making a double bond here. Just move the double bond. Okay, so I can write. This can exist like this. Any doubt in the first step? Okay. Now think, what will happen if I take this reaction with this starting material and heat it? What you can think now? You guys are now, just forget all these things. Just think, what is this? What molecule are this? Yes, nothing but your cyclobutane. So, what you have? You have 3 cyclobutenes, that is all. Molecule looks like really like different for you, but just close it and see, it is nothing but a cyclobutane. You have now 3 cyclobutane. So, it means you will have a 4, this is what 4N system, and you will have a 3 independent 4N ring opening, that is all. So, you will have a 3 independent ring opening, okay, 4N. So, you will have 1, 2, 3. So, how they ring open, okay, fine. 1, this can happen most of the time simultaneously, okay, synchronous. So, you can open this 3. So, you can have a nice 3 independent ring opening of your 4N system. So, you have 3 cyclobutane, that is all, okay, and they are, all these reactions happen independently, and it happens in the same time to give you the product. Now, write the product will be very interesting to write down once you open this. So, once I open this one, this, you just see the structure, it should be sort of 6-membered. So, I will get product like this. So, 1, 2, 3, 4, 5, 6. So, you have a 6-member, then the ring is open. So, this double bond and double bond. So, you have all the double bonds here, nice, see. So, initially once you give the, that is why I said once you give the structure, do not see the structure and get panicked, okay. Just observe the structure, concentrate on your pi system, that is all. It should be only on concentrating on your pi system. See, this reaction you have studied, nothing but is a 4N plus 2, that is a electrocyclic ring closure type of reaction, which you got this. Then it is what is again a ring opening reaction, which you know, which you have studied in detail. So, now you know it, clear, okay. Same way we will take another example, okay. This also is a nice sort of example which you have to study. Okay, I have a system like this. So, I have an hydrogen here, one hydrogen here, okay, clear. Now, I say I am going to photolyze this one. Now, tell me what will happen. First, tell me what system it is, and then define me what it is going to happen. First, you tell me what it is, whether it is you are expecting a ring closure or ring opening or sigmatropic, what you are going to expect from this system. I have a system like this, very nice system. So, what you are going to expect from this? Let me know. Very good. So, you get a nice electrocyclic ring opening, right. So, I can do this, very good ring opening reaction, you get a very nice ring opening. So, shall we write the product? Okay. So, what it should be, whether it is con or dis, yes, this, nice. So, that is over. So, your first step is over. See, once you understand that part, you just concentrate on your pi system, you are able to solve the one. Now, I have this molecule. Now, again I say that I have taken this molecule, I will say that I am going to heat this. What comes to your mind? what comes? Yes, it is nothing but it is a ring closure. So, what system it is? It is a 8 electron system. So, it is 4n, right. So, it is an 8 electron system basically. So, you will apply 4n. So, 4n what it says? 4n says for you con rotation. You know that now how to ring close, how to con rotate, you are clear with your hydrogens. So, there is no problem for you right now. So, now you see your hydrogens, they will be interesting to comment on. See, you see your starting material, okay. You have 2 hydrogens in the same plane. Now, you see they are in a 2 different places. What you did? You did one photolysis and you carried out an thermolysis and you completely changed their stereochemistry. See how beautiful it is. Clear? Okay. But you won't get this product alone. If you look the system carefully, okay, you can think about another product. I can say there will be, if you heat this, you might end up with another good product. What is that? That will be really interesting, because this since you are studying now electrocyclic reaction, yes, your mind is open for electrocyclic ring opening and electrocyclic ring closure. But see the system and you tell me like another interesting thing happened in this. What product it can be? Anyone? Any guess? See, the only problem is that you are not seeing the system, you are not numbering the pi. If you start numbering the pi electrons, you will know there is one important reaction which is well known reaction. See, just number this 1, okay, 2, 3, 1, 2, 3. What is again? Can you remember what is that? What you can think about? Yes, that's good. That's nothing but it's 3, 3 sigmatropic rearrangement. What is that 3, 3 sigmatropic rearrangement? What is that 3, 3 sigmatropic rearrangement? Anyone? Come on, man. Yeah, very good. Cope. It's nothing but you can, so it undergoes a nice Cope rearrangement. Just write the product. You have 1, 2, 3 system, 1, 2, 3 system. You can easily write the products. What it you can think about. So you can open, you have to close. That's all, right? Just have to push this electron. Right? So what you can write? Get opposite because it's opening like this. That's good. So that's all. So see how nice it has. See this pericyclic problem. Taken a system, you understood what is ring opening, then you understood what is ring closure. Then at the same time you have to see, because most of the time it's not going to give you one sort of product, this pi rotation. This might give you other product also. That's also you have to think on. That's why I took this example, because like you will be just doing this product, you will say that it undergoes a ring closure, but at the same time you should think, because it's a very good system for undergoing a 3, 3 sigmatropic, and that's why it can go Cope, and you know that Cope rearrangement happens very nicely, and so you get this 2 product for this problem. Clear? That's what, when you start doing problems in pericyclic reaction, you can then you know, like you will understand what the sigmatropic, all these things which you have studied individually. Now you can put them together and you can solve them. That's it, becomes more interesting. Okay. So, one more interesting application of electrocyclic reactions which you have to which this problem can let you know. See, there are molecules which we call them as molecular switches. Have anyone heard about it? Yes. See, what happens is that the molecule, there are different type of molecules which are known in literatures. Okay, they are called as molecular switches. What happens in response to the external stimuli, like it can be light, heat, or whatever it is. Okay, external stimuli, these molecules respond to the external stimuli and they change their physical properties. The more interesting of them is their color change. So, some of the molecules, if you see, they are very colorless. Okay, they will be colorless, but if you shine light, okay, the molecule turns into blue, green, violet. So, it becomes like really interesting. Just you have to take the molecule, okay, then you have to shine light, then immediately the molecule becomes blue. That is okay, because there are many molecules which can do that. Once it is colorless, it becomes blue. So, what about molecular switching is that once it becomes blue, okay, after shining light, if I heat, if I get the reversible, that again it becomes colorless. So, what happens once I shine light, it should become like blue, then once I switch off, then it becomes colorless. So, if it does this part of thing, then we call this as a switches. Yeah, just your switch. So, they are very interesting because most of these property the molecules have been used to change surface properties and everything, and photoresponsive molecules are very interesting because what happens, you make the molecule, you shine light on them, and then it becomes like whatever color you want, you design according to that, and then you heat it, it comes back to colorless state, or you can, or in room temperature it turns back. So, if you switch off the light, it can turn back. So, these are many nice systems which people are making, and they are useful in many surface properties which are used. Okay, they are called molecular switches, and this molecular switches basically you have to design molecules in such a way that the whole thing should be like a reversible. The reaction should be, you should keep in mind that this reaction should be reversible in nature. Okay, otherwise there is no switch property, right? So, how to think about reversible? Any reaction which you can just comes in your mind which is reversible you can think about. Any reactions? Yes, very good. It's a isomerization. Okay, you can take any isomerization. Okay, they are very good reversible. You take cis and becomes trans, and trans immediately will become cis depending upon your external stimuli. Cis can be blue color and trans can be yellow color, and then you can move from blue to yellow, then yellow to blue, depending, changing your switches. So, that's very interesting area which slowly evolved. Nowadays, there are certain molecules which also use electrocyclic reaction, because most of your electrocycle reactions are reversible, right? Because that you can do an electrocyclic ring opening, at the ring opening, then that reaction is again reversible, because you can ring close, then you can ring open. Then if you can design a molecule which can be colorless, once it is open the ring, it becomes colorful. Then what happens? If you heat, then the molecule will ring close, then it becomes colorless. So, you can make molecules like that. That's a very interesting area came out now. Okay, that's we call as molecular switches. Okay, so with that idea, I will give you one good example on molecular switches. Done on electrocyclic reactions, based on electrocyclic reactions. There are many reactions. Okay, just I am taking reactions which are based on electrocyclic reactions. Electro. Okay, this is a very good molecule. Okay, now if I take this molecule, okay, and if I photolyze this molecule is colorless. Fine, this molecule is colorless. So if I photolyze this molecule, what you can expect? So first you tell me what, leave over the molecular switches right now, tell me what reaction you are going to expect here. Whether you are going to think about any other sigmatropic, or you are going to think about electrocyclic or whatever. Anyone? Yes, you can think about electrocyclic ring opening. Where is that? What electrocyclic ring opening we are talking about? Yes, so you can nicely do this electrocyclic ring opening. See, now what happens once you ring open, it becomes a keto form, like ketone. And most of the time you know that it's not like, but ketoforms are chromophores and they have colorful nature, right? So it undergoes a nice ring opening reactions, and you know this ring opening reactions are all mostly nice and they are very simple to do. Nitro. So it should be nitro. Yes, NO2, and you have a double bond here with a ketonic form. And this is, if you see this one, this is initially it was colorless. Once the ring is open, this immediately becomes blue color. See, that's a nice part of it. I told you there are many examples where you have a colorless molecule on photolysis immediately becomes a blue color. Okay, that is fine. But if I take the same molecule and if I heat it, same photolysis molecule, on photolysis this opens up, it's a your 4n plus 2, you use this rule to open up this, it's an electrocyclic ring opening to give you a blue color, that is really good. But once you heat this molecule, what you are expect? What you are going to expect once you heat it? So 4n plus 2 ring closure, right? Just a ring closure reaction. So this blue color, once you heat, what happens? It immediately becomes the starting material, it becomes colorless. So that's the whole beauty of this reaction, is that like you take a colorless molecule, you photolyze them, immediately it becomes a blue color, okay? And then if you heat this molecule, it loses its blue color and becomes a colorless. That's because of your electrocyclic nature. What happens? Once you undergoes a ring opening, then it undergoes a nice ring closure. See, these are called as molecular switches, and you can, based on this, using this, people have, you can attach it to there are many biological studies which you can do with these molecules. You can attach to tagging with proteins. People are doing molecular switches in many fields. They are very interesting properties, okay, and they are coming out nicely. So you have to you can study about this. There are many review articles on molecular switches. I'm just giving a simple example on photolysis as well as for heating, but there are many good examples like cis-trans isomerization molecules are very they are doing molecular switches highly nice. Okay, so these are your some good examples of your molecular switches molecules. Okay. Now what we will do is that we will take a simple system, okay, which you will understand. Okay, it's a single bond. Okay, you have a system like this. Now what happens? Any idea what this system can do? Because why I want to take this example, you can use this example for continuation of other problems which I will let you know, like annulenes we can work on using this problem. So what happens here if I take this molecule and heat it? So what system it is? Yeah, it's a 4n plus 2 ring closure, but it's a two independent system happening together, right? So you get this nice product. So you get this product, okay, on heating. These are nicely reversible, okay. This is nothing but it's a 4n plus 2 cyclization. Very good example. So that's so what I am trying to do in the rest of the class is we will understand problems like this, okay, so that now we will know that how to use our knowledge of pericyclic and solve these problems. Clear? Okay. So today we will stop here, okay. In next class we will discuss other problems, okay. We have some other more problems which we will discuss in the next class. Thanks.